Yeah, thanks for coming today, the early morning, the final day of the workshop, and thanks to the organizers for inviting me. I'm happy for the opportunity to talk about this. I'd like to apologize for the slightly grandiose title, partly because in this talk I will barely talk either about atoms or algorithms at all. I'll be talking about the space in between, a sort of caricature of what's involved in building a quantum computer, a scalable quantum computer. There's a lot of excitement, of course, in quantum technologies these days about building quantum computers with large organizations such as Google and IBM and Intel setting forth their designs based on a very different principle than what I'll be telling you about today. It's very early days in quantum technologies, and there are a lot of details that you could get into. I'm not going to get too much into physics, partly because, well, while I've got a bit of a physicist's background, it's not my specialty. I've got a specialized role in a large project. I'll be telling you more about how you get from something like a quantum computer to something that you can program. So quantum computing, it's this interdisciplinary field that brings a lot of people together, but it's not really one field as it is 3 or 4 fields that are butting against each other. And so here we have somebody thinking about a circuit diagram such as people, my colleagues, would routinely think about. If you can't see the details of it, don't worry, because it's just basically collection of wires, a little bit like a tensor network, a little bit like a ZX diagram. And somebody might say, well, where are the atoms? Where's the physics going on here? And there are a bunch of sort of conflicting priorities and conflicting senses of when you've got a reasonable description of something that you could do with quantum physics. And then there's the additional complication that when you talk about people who would like to use these quantum computers or ways that you design algorithms, we don't really have a way that you can describe this that would be familiar to a programmer these days of conventional computer systems. The people who design the algorithms, they're much more like mathematicians than they are like programmers, and there are some historical reasons for this. But we want, of course, to try to get to the situation where we've got more practical programming than we have had up until now for quantum computers. So we've got this disconnect between at least 3 different groups, and these groups subdivide further still. So you've got the physicists. They think about such things as decoherence times the error budget, that is to say, they want to get their fundamental operations below a certain amount of error, and they can do trade-offs between where the sources of error are. And the gate fidelity, how well their individual operations work. If you wanted to think about what this would be like in conventional computing, that would be like inventing the transistor or worrying about the properties of the wires that we're using. Very, very, very low level basic physics. Computer scientists more in the field that I'm a member of, they're working with those abstract circuits where you say, okay, we suppose that we have qubits. We suppose that we have operations that are more or less good. We're aware that they may not be perfect, but if we know how imperfect they are, then we know we're able to rely on a certain quality of the operation afterwards when we compose them all together. And then they worry about unitary circuits and studying asymptotic speedups, which is like programming an assembly language. That is to say, not even having so much as for loops, doing jump if this register is equal to 0 and so on and so forth. And worrying about exactly how much error you get when you're doing calculations with floating point precision. Still pretty low level as far as the programmer goes, but miles above what the physicist is worried about. And then future users are thinking about things like improving route planning. And there I don't mean a technical piece of art, I mean like you have a car, possibly it's self-driving. You want to know how it's going to get from the airport, to the airport from your current location in current traffic conditions. And they just want to call a function from a library. They don't want to think about any of the details that came before that. What we need to do somehow is to sort of bridge the gaps in between these communities, not in terms of them talking to one another. They can be, you can think of them as playing specialist roles in designing a complicated system. But you need some way of bridging the gaps in between and ways of filling in the specialist roles in between. You need a roadmap for that. And ultimately, in order to get it so that we have a computer system that's usable by people who might actually have problems that can be solved with a quantum computer. So where we are now, as I suggested earlier, we've got, it's early days in quantum technologies. We've got processors with less than 0.01 kilobytes of memory. So this is, of course, I'm writing this facetiously. We don't measure memory in quantum computer in kilobytes. We don't even measure it in bytes. We measure it in bits. Essentially, you could give each of the bits an individual name and refer to them by name. And in practice, this is what you do when you actually write the algorithms, when you write the circuits. You actually deal with the fact that you're dealing with a very specific bit which you're going to get to talk to a very specific other bit. No variables as such. We don't allocate variables to spaces, to places in memory in a way that a compiler does. This is something that we want to do eventually, possibly even soon, but we aren't doing this. This is just to give you an idea of how far we are from the usual regime for programming. For those of you who do any sort of simulation in your code, you know that this is not how you work. This is not how you should work, except that we need to get to the point where we can do things in a more manageable way. And the users don't care about any of these details. They just want to get on with things. And they're sort of expecting us to have coding standards already for quantum computers. Well, we'll be able to borrow some from classical programming, of course. But yeah, basically just to give you an idea of where we are, that the fact that the potential users don't even really have an appreciation of this situation. So what's my role in this? I'm here essentially as a representative of the Network Quantum Information Technologies project. So the UK has a few quantum technologies projects on things like communications and sensing, where they think that quantum information and quantum physics might be able to be an advantage. This is one of those projects as part of this more general program. And yeah, in this case, we want to build devices in NKIT in particular for networking and for computation. So devices, we really mean like one sort of module or two modules, two different kinds of modules that you can build over and over and over again and configure in different ways, either to make a computer or indeed to make a network. Basically, a way that you can do communication from, let's say, from here to Edinburgh, in order to do protocols, communication protocols that involve entanglement. And you would need a chain of something like repeater stations along the ways. And these repeater stations would consist of the same simple devices as we were trying to build a quantum computer out of. It motivates a very different design principle than, let's say, IBM or Intel are thinking of. And, well, I have a physics background, but I'm not a physicist. It's been almost 20 years now since the last time that I solved the Schrödinger equation. My role here is as a computer scientist, being aware of the general theory, thinking about things from first principles. Okay, supposing that we've got a given quality of hardware, there's more to quantum computing than just worrying about the circuit, because you do have to worry about reducing the noise. Thinking about all the steps in between and thinking about how that might affect the way that you're going to do things with your quantum computing system. So essentially, you could say that I think the sexy term for this in Silicon Valley is full stack. Building this stack from the bottom to the top. Bridging the descriptions, where we have the hardware modules. We talk about, given the hardware model, how we're going to deal with error correction, how the error correction motivates particular architectures. And by architectures, I just mean how you're going to arrange the modules in space, have them interacting with one another. What these architectures motivate in terms of higher level operations, that is to say operations on encoded data, where you have the freedom to pretend that they're noiseless because the noise is sufficiently low that it's a small white lie. And then whether or not this gives you an idea of programming strategies. We can put this into a sort of a metaphor of building up from meaning. If we think of meaning as a way that you can organize the details of the world into coherent narratives, well, it still has to cohere with basically what emerges out of the reality. So taking a look at how we aggregate these pieces together into larger and larger structures until we have something intelligible. Okay, so I'll go over a little bit about the hardware model. I'm not going to be talking very much about physics because, as I said, well, I certainly don't expect, some of us have a physics background here, but none of us are going to really want to talk too much about what happens with electron energy flows and ions. I may occasionally refer to some of the things in the NKIT hardware as ion traps, simply out of a force of habit. It's not important that you think of them as ion traps. It's not important that you be aware of ions in particular generally. Basically, it's going to be focused on a modular approach that involves collections of qubits. So here, I don't know actually, we talked quite a bit about quantum information here and non-commuting observables, non-commuting projectors, but just as a show of hands, how many people are comfortable with the term qubit generally? Okay. So, I mean, a qubit is just a quantum bit where you've got, for example, you've got a standard basis where you've got a 0 and a 1. You've got more than one basis, so there's more than one incompatible way of storing information, but no matter which way you store that information, you can store one bit of information, a 0 or a 1. I'll talk a little bit later about observables and anti-commuting observables. And that will at least be broadly familiar to all of you, I would expect. Again, I'm not going to be relying on a lot of technical knowledge. In fact, you could probably see this as basically a landscape painting in a sort of impressionist style of basically what people in quantum information, when they're dealing with quantum technologies, at least, what they talk about and the way that they talk about it. And some of it is, I think, sympathetic to the way that you deal with way that you deal with interventions in this field, where you may not have access in general to much information about the state because you're dealing with complicated information. You deal with it in a top-down way in the notion of non-commuting observables, and there are certain aspects of this line of research which also thinks in that way. We do have, in principle, access to a notion of what the quantum state is precisely, but it's not fruitful to necessarily obsess about that either. So I'll try to be talking about this on a high level. In particular, we think of qubits as either a physical system that can store a certain amount of data, or that unit of data itself, as you would do with a bit. A bit can either be a physical system that stores a 0 or 1, or it could be the 0 or the 1 itself. I'll sometimes conflate between the two. Hopefully it will be clear from context what I mean. And these physical systems that I'll be talking about, they could be simple physical systems, but eventually they will become large physical systems that still only store 1 qubit. The reason for this is because that's how you go about doing quantum error correction. And the operations that we perform, of course, in order to build a computer, you're going to want to have some sort of control over what it does. But your control is going to be imperfect. The operations that you do won't necessarily be precisely what you want. You want to go to your head over that. Most of the time in quantum computing, we talk about unitary operations. I'm going to be talking about things that aren't necessarily unitary. And I'll hopefully it will be clear when that's happening, and I'll try to give an account of what's going on with that. So the building blocks for what MKIT wants to do. We want to, as I said, we're building ion traps, but it's not important that you think of them as ions. You can think of them as just linear boxes containing a collection of qubits. And in this case, we want a handful of qubits. The experimentalists get a little bit nervous when anybody suggests that they might want to have more than 10. So we're dealing with very small modules. And in particular, what they want to do is they want to build a very small module very, very well. To have very high quality modules and to be able to get a notion of scalability from the ability to produce many of them. And if you want to produce many of them, having them be small and simple is an advantage. Eventually, you're going to need to have the many modules if you want to have scalable quantum computation, because you're going to need many qubits. And if each box only contains a small number of qubits, you're going to need many of the modules. Within the modules, we're assuming that you have the standard array of things that a quantum physicist or a quantum computer scientist would want when you're working with qubits. You'll have a small array of single qubit operations and 2 qubit operations that you can perform. We've got specific implementations for these. We know exactly how we want to realize, let's say, a controlled NOT gate, if you know what that is. I won't go into the detail of that. But basically the standard recipe of things that you would want from an ideal quantum computer, and we're sort of allowing them within these ion traps, but only between adjacent qubits when we're dealing with 2 qubits. So linear nearest neighbor, if you know what that is. The way that we get the scalability, as I suggested, we're going to want to build many modules, and the modules are going to communicate with one another. So these modules will have classical control systems. There will be classical computers coming along for the ride, and they'll be communicating with each other using fairly conventional technology. There will also be quantum communication. In particular, one of the qubits, the ions indeed, will be able to emit a photon, basically just a quantum of light, in order to try to build entanglement in between the 2 modules. It's a dedicated qubit for doing that, and that's basically part of the architectural constraints. So we think of this as a facility that each module has to form some entanglement with another module. That didn't quite work properly, but yeah, we're going to want this entanglement making facility to be switchable so that for one module it can choose to try to build entanglement with a particular other module. And there's the question of how complicated this network of entanglement making is. We'll want it to be relatively simple, but we have some flexibility. These modules can be far away from one another. Because we're using light, we can use fiber optic cable, we can sort of wire things at longer distances. There will be some limitations eventually. We won't want to go completely crazy. Like if we have, let us say, 1,000 or 1,000,000 of these modules, we won't want to have the complete graph between them. We won't want to have complete connectivity. We'll want a more clever and more scalable architecture than that. But, for example, we don't need a planar graph. We don't need to restrict ourselves to a planar graph. These details are ultimately not important. Actually, it would be enough if we were absolutely forced to just have a nice rectangular grid of connections where each of the sites on the grid was some module, and only adjacent modules could communicate with one another. That would be enough for our purposes. We just expect to be able to do more. So we have this entanglement making facility between pairs of modules. The entanglement that we get is not necessarily very good, though. I mean, you know that we've got the Bell inequality, and one of the features of quantum mechanics is that you can violate the Bell inequality. But just because you can violate it doesn't mean that you violated it maximum. You can violate it only by a little bit. And this corresponds to the quality, so to speak, of the entanglement, the extent to which the correlations in the measurement outcomes on the entanglement state on either side has stronger correlations than we would expect classically. That's going to be important when we want to try to build scalable quantum computing. We want near to maximal Bell violations, and in particular, we want maximal Bell violations with specific observables. So not just any maximally entangled state, because again, there's a continuum of them. We want to have some fixed particular Bell state, some fixed maximally entangled state that we're generating between them. We have to work to do that. So that motivates a sort of division of labor within each of these modules. We've got, here I've sketched out, we've got a red qubit on the far right. That's the one that's actually implicated in generating the entanglement. And then we want to do something that's called entanglement distillation. And here the analogy, the term was suggested as an analogy to the distillation, let's say, of alcohol, where you've got basically a process of stages where you try to take something which is rather impure and you make it purer. You have to throw away some of the material that you use, so you have some waste product. In this case, the waste product will be that some of the entangled states that you get, you throw away. So you use a large number, not very large, but a largish number of rather mediocre entangled states in order to create entangled states that have pretty good entanglement. Okay, so just as a caricature of what this looks like in practice. So here we've got something. This represents what's happening in that module. There's another module someplace else where there's corresponding events happening. But in one module, you create one half of a mediocre quality entangled pair. And then you swap that around, and you create another copy of a mediocre entangled pair. Then you do a joint operation in between these two copies. That joint operation gives you, with some probability, good probability, half of an entangled pair that has somewhat better quality. And you move that up the ladder, you do some more generation of entanglement, you do some more distillation of low quality entanglement, you get another copy of the entangled, medium quality entangled state. And then you distill that, and so on and so forth. You sort of climb the ladder of quality of entanglement. So these are non-deterministic. That's non-deterministic in the physicist sense, which is to say, it's not guaranteed to succeed, but you do know when you have succeeded. And in this case, we want in particular that the probability of success is reasonable. If the probability of success were low, then you would expect this to be wasteful, that you would require an enormous amount of entanglement in order to succeed. And the lower quality that you have initially, the harder you do have to work in order to get good quality entanglement, as you might expect. So when I say mediocre, the sort of quality of entanglement that we expect to get in the lab, I mean, I can throw a number at you. Basically, you can certainly generate something with fidelity 0.9 to the best state. If you don't know what that means, don't worry too much, but you can think of that as sort of a percentage of quality. 0.9 is 90%, that's not too bad. We want to have something where we're counting the number of nines. So 99% would be 2 nines. Ideally, we want 3 or 4 nines of quality. So to 1 part in 10,000. So we've got this distillation procedure. And now, as good engineers do, you say, okay, you've got this ability to do something. We now do our best to forget about it. We just rely on the fact that we can do this. And forevermore, we just think about the fact that we've got this higher level facility which acts as though it's perfect or nearly perfect. Okay, so we've got these modules that we want to connect with one another. We've got a way of making entanglements, albeit somewhat involved, but you don't have to worry too much about the details anymore. In order to get scalable quantum computing, we're going to need many modules, and we're going to need to build lots of entanglement links as we're doing the computation. So they're necessary to do anything interesting, but they're slow compared to not only all the rest of the things that you do with these modules. Things within the modules are generally fast on the scale of milliseconds, and that's only the results of a couple of years ago. We're getting much faster with these operations as well. But it's all for nothing until you can generate entanglement in between the modules. And that happens at a rate which is thousands of times slower at the time. So, we've got these average times for creating the mediocre entanglement, so that's on the order of 1/10 of a second. You need something like 10 copies to build a reasonable entanglement link, so now we're dealing with on the level of seconds, not even hertz in terms of generation of entanglement. Something you have to worry about with quantum information is the half-life of the information. There's a sort of a decay process where you can think of the information as being corrupted with time. And it's a random process, and so it has a half-life as nuclear materials do, or indeed as paper has. And the problem is, so we can compare these two timescales. You can see that you can just about fit 25 two-module operations within one half-life of the system. So you're going to need to do something to protect the information, to extend it beyond the half-life of the system. And that's going to require error correction. So the challenge is, given this, is to play for time within each module. We only have so much time before the data corrupts while we're building these entanglements. We want to delay the corruption process, to slow it down just enough so that we can make good use of the entanglement. Once we have the entanglement, we want to use that to do further suppression of noise. And then there's the separate question of how we should arrange these modules in relationship to one another so that we can have a scalable way to actually build a computer and have a reasonable expectation that we can do useful operations with them. So, the second stage is now away from the hardware and what we would expect to do with the hardware. So, quantum error detection. So this is not a new result actually, it's from 1994, but it still catches some people off guard that quantum computing sort of has the features of an analog model of computation. Analog computation is notoriously unstable, and in particular you might think, well, if the error is consistent changes in the amplitudes, how are you going to know that you've got a problem in your amplitudes? How are you going to be able to detect the errors on your qubits if you've got this continuous model of computation? The answer is that quantum computation is, for all of its apparent continuity, it's secretly a discrete model of computation. I mean, it's not just because you've got qubits, which are discrete units of information, but because you can treat them very much as bits in certain respects, bits in which you can access the information in different incompatible bases. And by using the fact that you can access them in different incompatible bases, you can then incidentally protect superpositions of these bases. So what you do if you want to protect your information is you take a qubit state and you encode it as a two-dimensional subspace of a much larger system. And how you define these subspaces, if you want to do it in a practical way, you define them in terms of correlations in between the qubits. So Pauli spin operators, I'm not going to assume that most of you know much about Pauli spin operators. I'm actually going to tell you a little bit about them. So here we've got Z and X matrices, that's just the normal tensor product. So the Z matrix, you can think of as basically describing a feature of the standard basis. I may as well write it here, actually. So this is the Z matrix, and we're thinking of this as an observable with respect to you want to measure. And so we're interested in the eigenvectors of this matrix, which are just the state 0 and the state 1. And they've got eigenvalues plus and minus 1. If you think about this as something that you can measure, it distinguishes them by the different eigenvalues, which would correspond to different measurement outcomes. So you can think of Z as a shorthand for describing the standard basis. Might be an unusually algebraic shorthand, but it's a shorthand. Also up on the board there, I've got the X operator, which is this matrix. You might be more familiar with this as the not operator, but here I'm not thinking of it as an evolution, but actually again as an observable. And this distinguishes the two states plus and minus. That's a proportionality symbol there. So it's representing two incompatible ways in which you can access information out of a qubit. And the way that you would access it is, for example, by performing measurements. Now, I've got these tensor products of these, and I'm suggesting that these are observables. These are, again, going to be Hermitian operators. They're going to be operators that have eigenvalues plus 1 and minus 1, in fact. So they are also things that you can measure, but if you were to talk about measuring this operator, that's not the same as measuring qubit 3 and also measuring qubit 4. It's about measuring coherently, so to speak, the parity of qubits 3 and 4. So this will distinguish the states 0, 0 from 0, 1 on qubits 3 and 4. But it would not distinguish the states 0, 0 and 1, 1, both of which are even parity states. And in particular, superpositions of 0, 0 and 1 are also even parity states. So performing a measurement with respect to this will collapse any superpositions between even parity states and odd parity states, but it will not collapse any superpositions within the even parity subspace or within the odd parity subspace. And we can take advantage of this to encode quantum information. Here we've got the same thing for qubits 1 and 2, and here we've got a 4-particle measurement that would be basically talking about the properties of the parity, now in this basis instead of the standard basis, of the entire system. Taking this approach, this is what's known as stabilizer coding in error correction codes. And it allows you to borrow from the theory of linear error correction codes in classical computation, which is also concerned with encoding information in a subspace of Z2 to the n, where n is the number of bits. Encoding it in a subspace which also have known and determined parity properties. We're going to take advantage of the same intuitions for parity properties in order to encode quantum information. Now you might say, okay, this sounds well and good, maybe a bit algebraic, maybe a bit abstract. How do you actually use this to detect errors? Well, in this case, what we're going to do is we're going to detect changes or violations of the parity properties that we set out to begin with. So suppose that you have some error that happens on the third qubit. What do you expect? So this is going to perturb the state. The parity properties that you had initially may no longer hold. What you're going to do is you're going to measure the correlations. I mean, you're actually going to perform the measurement of this observable. That may be an aggregate procedure. You may have to do some unitary transformations to achieve that, but that's a thing that you can in principle do, and in practice you can do. You're going to measure these observables. If no errors occurred, then performing those measurements won't disturb your state at all, because your state already had a definite value of each of those parities. If something has happened to your state, then you're going to have a collapse of your state into either no error or some error. And in this particular case, any error that happened would either affect this parity property, violated its status, or this parity property violated its status. So if we measured that either of these parities are no longer the one that you expected, we know that some errors occurred. If you've got a sufficiently well-designed collection of these parity properties, you can not only detect what that an error has occurred, but you could detect what error has occurred and how to fix it. You can't correct arbitrary errors that occur, but all that you want is that you can detect the errors that are likely to occur. You might also ask, okay, well, can we say that the encoded qubit exists somewhere in this system? And the way that we talk about how to use the encoded qubit is by its observable properties. That is to say, by measurements that you can perform, measurements that you can perform that would actually affect the encoded state, and ones that correspond again to a sort of encoded set or encoded X measurement. So that is to say, in this more complicated system that has many degrees of freedom, you identify one degree of freedom that corresponds to the encoded information, and you can represent that encoded degree of freedom by an operator, actually a pair of operators that don't commute with one another, but which do preserve all these parity properties. So something that I didn't mention, we worry a lot about commutation properties in quantum information theory. These two operators, they don't commute with one another. More precisely, they anti-commute with one another. So that means that not only do they have, not only are they incompatible as observables, but if you think of this as because they also happen to be unitary, if this is an operation that you perform on this, it will flip in between the two possible outcomes. In this case, so we've got this logical operation. It commutes with all three of these operations because X anti-commutes with Z. So if you try to commute them, you end up with a phase of -1. Well, you have a pair of them, you end up with a phase of -1 twice, and they commute. So this is a degree of freedom which is consistent with all the constraints that you've imposed on your encoded qubit, and it's a degree of freedom which is not entailed by all the constraints that you put on the qubit. It's a degree of freedom that actually encodes some information about your qubit. We think of it as representing an encoded version of this X operator. So we think of this encoded qubit as being some abstract object where this is now an interface by which you can access the information that you would normally think of as being associated with that operator. Similarly, we'll have an encoded version of the Z operator, and it's important that these two operators don't commute with one another because they represent encoded versions of these two operators which don't commute with one another. In particular, those two operators should anti-commute, and you can see that they do, because the only place where they act in common is on this one qubit. If you try to commute the operators past each other, you get an anti-commutation from this tensor factor, and you say that they anti-commute. So they end up being a way that you can access the information in the encoded quantum bit, just from the more abstract property of having two observables that don't commute with one another, and in particular have the specific property of anti-commute with one another. You might suspect, well, okay, the only place where they act in common is the second qubit. Is that where the encoded qubit lives? The answer is, well, no, not quite. This second operator there is something which is equivalent to this first operator. That's because these two operators are related to each other by the fact that their product is just the same as this parity property that you've imposed on your entire system. So they're equivalent properties as far as measurable information goes. So if you were to suspect that it lived on the second qubit from the first and the third red lines, you could equally well conclude that it lives on the third qubit because of the second and the third lines. In practice, the qubit is distributed evenly, so to speak. Not symmetrically because there's a difference in status between the X's and the Z's, but it's distributed evenly over the entire system. So there's no a privileged location where this qubit lives, and actually that's what you would hope for, because if there was a privileged location, you could probably affect the encoded qubit more easily just by having an error on that one location. Okay, so that was just sort of a broad overview of quantum error correction that I thought you might be interested in because of some of the consonances with how you access information abstractly with your data in very complicated systems such as humans. The sorts of errors that we expect to have in our modules is something called coherence loss, where you've got superpositions of the standard basis looking more and more just like a random sampling over the standard basis, where the information that is accessible through this X operator sort of gets suppressed with time and it sort of decays exponentially. Coherence loss corresponds to the presence of just one type of spin error, the Z error, that is to say where you have some probability of this as an evolution occur. Because you have just one kind of error, it's sort of an error in exactly one basis, and you can treat this error as if it was classical, so to speak. A classical error specifically with respect to this basis, the x basis. So classical not in the sense of its mathematical representation, but in the sense that it has a privileged basis. And so you can just use classical techniques such as the classical repetition code. So this is just saying that we want a property of the state that the parity of the second 2 bits is equal to 0, the parity of the first 2 bits is equal to 0. If you think of a repetition code, I don't know if that seems like a bit of jargon, but all I mean is just where, with classical information, if you want to say 0 and you want to be quite sure that you're understood, you say 0, 0, 0. If you want to say 1, you say 1, 1, 1. And even if somebody mishears one of them, they can take a majority vote to see which one you actually meant. So this has the property that if you take the parity of any 2 of the bits, you have 0. And that's exactly the property that I'm looking for here. If you have one Z error, for the same reason as I described there, you can do something like taking the majority vote. Or in particular, you can see, well, which are the pair of qubits that don't have the correct parity properties. If you have an error just on the first qubit, you say, okay, well, this second parity property is violated. The anti-commutation would give rise to a change in the parity there, and you can see this parity is no longer what I expect. This is the problem, basically, with that parity. If it occurred on the second qubit, you'd say, okay, that other constraint is now violated. If it happened on the third qubit, well, both of those constraints are violated. The important thing to notice is that depending on which qubit it happened, you get a different signature, and that allows you to determine which error happened, and you can correct it. So it sort of motivates a way that we use, again, to perform a division of labor of the qubits within the modules. We would want to have 3 qubits within each module, encoding 1 logical qubit of information. And then we'll have this effective link generating facility still. We would do this with other modules, and then they'd be in communication. The entanglements that you generate in between these two can be used to mediate interactions in between these encoded qubits. One way that you could do this in principle is by teleporting the qubit from one module to another. In practice, that's not what you would actually do, because it provides too many opportunities for the information of a qubit to be corrupted and shuttling it back and forth. But you can also do what's called teleportation of gates, which is a related phenomenon. I won't get into details about that, but where you can use entanglement to mediate 2 qubit interactions, even if those qubits are far away from one another. So in this encoding scheme, it's actually a reasonable way to do things. You can easily initialize states, simulate transformations within each module and between modules, and measurements. The measurements that you want to perform when you want to get the outcome to your computation. Now, the coherence loss that we get may be due to correlated spin errors. I sort of suggested that errors come one at a time. Of course, it's more of a Poisson process. But in particular, there's no reason a priori to assume that they come one at a time. They could come systematically all at once on all the qubits, which would be a bit of a problem for something like the repetition code. If you flip all the bits at once, you're going to have a perfect confusion about what your information is. So in this case, it's something which would be a continuous process. You don't expect suddenly for all of your qubits at once to be affected. But you're going to expect a slow rotation of all of your qubits at once and in synchrony with one another. And what's worse, at a rate that changes with time in a way that you don't have a perfect handle on. You want somehow to accommodate that. And the errors, if you measured often enough and quickly enough, you could catch it before you had a significant accumulation of errors. But that error correction process itself is going to be noisy. You have imperfect operations even in your error correction. And so you're going to have a faster accumulation of errors. Fortunately, you can actually take advantage of the correlation in the noise. You can make it so that the correlation in these rotations is something that the correlations in the state are immune to. And in this case, you would do it by anti-correlating the states of the qubits. So that's what that minus sign corresponds to. Instead of selecting to have even parity in the standard basis, you select to have odd parity in the standard basis, and superpositions of states that have odd parity in the standard basis. So that would actually give you an economy. You can now use 2 qubits in each module to simulate one encoded, one logical qubit. So you get an economy. Actually, if in an idealized model where you have this particular error process and you manage to encode this would actually make the noise completely invisible to your system. Not only would it sort of protect somewhat, it would protect completely. Now, that's not the only source of the errors, that's just the dominant source of the errors. So there's still more work that we're going to have to do, but it sort of motivates paying careful attention to what precisely the noise model is and taking advantage of that with your error correction. And even we can even use this to at least detect the existence of other errors by, if we consider one of the noise processes that's less important, but which is not invisible to this, well, we can simply measure to see whether this anti-correlation property still holds from time to time. If we see that it's failed, we know that some other errors happened. We won't be able to correct it, but at least we'll know. And it can be caught at some higher level of error correction. Okay, so this is sort of a sketch of what you would do for error correction within each module. You're going to need to perform error correction between the modules as well. And you're going to need to do it in such a way that not only do you reduce the error, but in principle you could have the level of noise approach 0. We want to be in the same sort of situation that we are with classical computers, where you can just write an algorithm and not worry that your algorithm is too long. You might worry that it's too long because you want to go for lunch or because you have a deadline to meet, but you don't want to have to worry that it's too long and therefore you're going to get the wrong answer. That's just not what we want. So we're spoiled with classical computers. We've got very good engineers who've been working for decades on this. And now we can effectively pretend that they're perfect, except for the existence of Windows, say. But yeah, you can trust that any errors are errors of the logic itself and not errors of the mechanism. We want to get to the same sort of situation, so we want to be able to suppress the level of noise to 0 in principle, or as close to 0 as we want, just by making a larger system or by organizing it better. And we want to be able to do this for an unbounded number of logical qubits, each represented by one module. And again, it's helpful if the qubits, if you're situating them in space, that they aren't very far from one another. You don't need to have one qubit here talking to another qubit that's situated, say, in Grenoble to get your algorithm to work. You want them at least to be in the same room. Incidentally, yeah, we haven't really been talking about the scale of these things. We are going to be re-entering the world of computers that fills rooms, at least for a while. Miniaturization is a completely different issue from anything that I've been talking about here. Google, Intel, and IBM, they're all trying to bootstrap off of the existing technology for producing semiconductor computing. So they're going to be wanting to have computers that are miniaturized simply because they're using the same processes. With us, it's going to be a bit bulky for a while. The question is, which is the technology that's going to scale, regardless of how large the actual computers are? We're hoping to get scalability first and miniaturization second. And therefore, we do actually have to worry about the spatial, how far away qubits are from one another. Having said that, even though these qubits are very close to one another on IBM and Intel's chips, they're very restricted by a sort of planar topology. So even one qubit that's 1 micron away is too far away because there's too much in between. They're restricted to a very planar topology. So not just in our platform, but in other hardware platforms, this idea of nearness of spatial locality is very important. So yeah, from now on, basically we're going to be able to sort of forget what I told you about the hardware. We can treat each of the modules as a qubit, usually depicted by a circle. It'll be situated somewhere in space and they'll be interacting with one another in some way. And if you want to, you can remember that these circles correspond to modules which correspond to ion traps. But we're trying to climb the ladder of abstraction so that we can forget about the nitty-gritty details and focus on the next step up. And it's important for us that these 2-qubit operations, I mentioned they're coming out of the these entanglement links. These entanglement links are non-deterministic. We don't have to think any more about the distillation, but we do have to remember that these entanglement links are non-deterministic.
Why?
Can I, sorry?
Can you explain why they're not deterministic?
They come out of detections of coincidences of photons in photodetectors. So your photons will sometimes get lost, and so you don't know when you will succeed on those grounds. Your detectors are somewhat inefficient, so you don't know when that's going to happen. And then there's the distillation process. You've got the noisy qubits, and every time that you do some distillation, there's some probability of failure. That, again, with the analogy to alcohol distillation, that's a question of waste product. In this question, the waste product is the fact that there's a significant chance that your entangled states will not end up being useful. So you have a good handle on the expected time with which you can generate an entanglement link, but it's a probabilistic process. It's fail-safe in the sense that if you try to perform a 2-qubit operation, you may not succeed, but at least nothing has happened to your state, and you can repeat it, wait until you eventually succeed, try again. That motivates organizing our computation in such a way that you don't rely on performing too many of these 2-qubit gates all at once and requiring them all to succeed. So this is moving on to now how you try to organize error correction between these modules, now with sort of more abstract qubits. Not perfect yet, but better than they were before. So what are the preferred technologies for this? I say technology, people haven't built them yet. We just expect to. Technology in the abstract sense is surface codes. It's another error correction code. We arrange qubits on the edges of a square lattice. And we sort of impose constraints on the parities, as I suggested before. We impose them in this very sort of geometrically pleasant way, corresponding to the faces of the lattice. And sometimes we've got one that's, usually they're between 4, when we've got some boundary conditions that may be between 3 or 2 qubits. But parity conditions in a very regular way, essentially on a checkerboard or chessboard pattern. So those are our parities that we impose on the standard basis. We've got other parities that we impose on this plus-minus basis. You need to have both if you want to have correct protection against all sorts of errors that can happen to a qubit. But we have this nice pattern of parities that we impose, and it realizes some symmetries on the system. So the correlations, the parities that we impose, it basically makes the different errors that can occur, they can be equivalent to one another in particular ways, corresponding to topology. If you imagine that some chain of errors, say a chain of a particular kind of errors, say X errors, if they happen along some chain, then it doesn't matter actually which path between the two endpoints it takes. All the possible ways that you can connect to sites by a chain of identical errors will be equivalent to one another, and that's just down to the symmetries produced by the parities, the parity relations between all your qubits. So despite the fact that it's a discrete system, it's manifestly discrete, you can sort of think of it as a caricature of a continuous system with nice topological properties. So it corrects chains of spin errors, and in particular, if you want to have an undetectable error, it has to be one that spans the entire system, which is the reason why these seem so promising. You need to have a global conspiracy of errors in order to have something that you cannot correct. The logical operators, the ZL and XL that I was mentioning a little bit for the correction of the modules, are exactly such chains that span the size of the system. So you could think of a chain of Z errors that happens as an operation, as an error that you want to avoid. But given that they're going to be rare, you can also think of it as a way that you can access information that you can make use of, constructive use of. So you'll have one way of accessing the information of the qubit that represents how you would access the standard basis of the encoded qubit. You've got another way that you can access the plus-minus basis, the conjugate basis of your encoded qubit. And we think about the system now in this high level. We now start to forget about even the individual qubits and think about the system as an aggregate with nice topological properties. It's the most promising known in quantum error correction code, not just because it has nice mathematical properties. There's a question of error thresholds. What error rate can you expect to protect against? This has the highest known error threshold of something like 1%. So if your error rate is substantially less than 1%, you just use this code, and then you can essentially reduce the error rate to as low as you like. So yeah, I've suggested that topology is important here, but in particular, it's fairly general. I've drawn a square memory here, but there's no requirement that your memory is encoded in such a way or square. They can be rectangular or even non-rectangular, just so long as you've got these parity properties arranged in this uniform checkerboard way. Smooth deformations of the code, you can sort of stretch, so to speak, your memory. The way that you stretch your memory is by adding rows of qubits and imposing parity conditions. And discontinuous deformations, such as tearing, for example, or merging two pieces together, stitching, can be used to realize computation, so non-trivial transformations of your data. So surface code merging, what does it mean to merge two of these patches? Okay, so here's some of the x observables and the z observables of these two different memories. They're just individual entities on the right. One on the left and two on the right from the indexing. We prepare some auxiliary qubits. It's not going to be terribly important, but we then sort of interact these two patches together with the auxiliary qubits, and we impose these new parity conditions, which involve the new qubits. So the parity conditions which didn't obtain before. We impose them by performing measurements and doing some small corrections if we find that we don't get the right outcome, but it's not difficult to do. And then we've got these, so those are the blue parity conditions that we've imposed. Now we impose these pink X parity conditions. This parity condition here does not commute with this operator, it anti-commutes. So this property of this memory, in as much as it was well defined before, it won't be well defined after. The same holds for this. If this was in a well defined state before this individual memory, after this parity constraint is imposed, it won't be well defined after. But the product of the two will commute with that parity condition and it will be well defined. So we perform this measurement and we get this new aggregate property. This new aggregate property is sort of, you can see it's got the same sort of general shape. It's going to be the logical Z observable of this new larger memory. And what we have is the Z property of that new larger memory is a combination of what happened for a product of the Z properties of the two systems that we merged together, the two input systems. And this is sort of a schematic representation. Yeah, sorry if that's difficult to see. Those blue nodes have Z's in them, and then we've got this pink node, which is just an abstract representation of this merge operation. Right, so we impose all the other pink parity conditions, and now we see, well, these two are topologically identical chains. They both change from the bottom to the top. There's no real distinction between them. As far as the topology of the system goes, you can translate it back and forth, and it should change the meaning. So that is to say that the logical X operator of either of the inputs is equivalent to the logical X operator of the output. Okay, so I mean, what does all this mean here? In particular, what does this mean that this is a 2-to-1 operation? Well, this is manifestly not reversible. I mean, most people, when they talk about quantum computation, they want to think about reversible operations or unitary operations. What's going on here? Well, it is definitely a non-unitary operation. It's going to involve measurements and you're going to lose a degree of freedom. But that's not to say that it's not something that you can do with quantum information. So this is a partial description of what's called a CPTP map. So completely positive, just meaning that it maps density operators to density operators. And trace preserving, which is to say that it preserves probability. It's a well-known and well-understood generalization of unitary transformations that correspond to all of those operations that are valid under quantum mechanics in principle. The way that you would often realize them, is by performing a unitary operation and then tracing away one of the systems that are throwing it away erasing it, initializing it to some completely independent state, something like that. But more abstractly, you can just think of CPTP maps as the proper subject matter of quantum computing. It's a partial description because I've cheated and I've not told you about the thing that can happen non-deterministically. There are two possible ways that this can go. The other way is basically closely related to this. I'm not going to go into those details. But you can come up with a CPTP map that's more or less described by these relations here. The one on the left involving the relationships between the Z operators, and the one on the right involving the relationships between the X operators. Splitting is going to look essentially like the reverse. So that was a horizontal merge, just for variety. I'm going to show you a vertical split. So you've got one memory. It's a rectangular memory. We can have rectangular memories. Here we've got two representations of the same Z observable. That is to say, two different ways of accessing exactly the same information about this memory. And here's the way that you would access the X observable. The way that you split is you perform some measurements of, in this case it will be this row of qubits. You're going to disrupt the existing parity relations in order to allow yourself to have two independent systems. So you'll have some measurements. Those blue parity relations, they've disappeared because they're no longer parity relationships that hold. And you throw those qubits away. And now you think of that one large aggregate system, you can now treat these as two different halves, independent of one another. Their states may be correlated, but we think of them as now different subsystems that you can act on separately. Those two representations of that one logical operator now correspond to logical operations on two different memories entirely. And so that's just to say that if your initial initial memory, you called that an encoded qubit 0, the Z operator on that qubit 0 now corresponds to the Z operators, the Z observables, on both of the child memories that have come out of this little procedure. You may notice this as being something like the inverse of what I showed for the X operators in that horizontal merge. That long chain X observable, well, nothing has actually happened to it at all in this whole process. But we see that it's the product of these X observables on these child memories. And so we've got that relationship on the right. So what I showed you before with the merging was a partial description of the CPTP map. This is actually a complete description of the CPTP map, which happens with this procedure. So it perfectly characterizes some operation. And it's a 1-to-2 operation. This is something that would be used for quantum computer scientists. But again, it's not just a unitary bijection. So these splits and merges together are techniques that are known as lattice surgery. There are ways that you can realize two qubit operations, that is to say things like a controlled knot, in between these surface codes, these surface memories. In particular, so they involve quite a few operations, quite a few two qubit operations in between these nodes. But the number of operations scales. You're performing operations to merge the boundaries and to split the boundaries. It scales like the length of the boundary. It scales like one of the dimensions of the system. The other natural way that you could perform something like a control knot, a two qubit operation, is to perform, if you have a patch like this, a patch like this, well, you could put the qubits in one-to-one correspondence with one another in the obvious way, in a sort of geometrically reasonable way, and perform control knot operations directly between the two. But if you do that, the number of two qubit operations that you require scales like the volume of these surfaces and not like the boundaries. So the advantage to doing it this way, well, so for the people who are actually constrained to planar systems like IBM and Google, they would more or less have to do something like this if they were dealing with surface codes. For us, it's advantageous simply because it allows us to reduce the amount of non-determinism. So these abstract diagrams that I've been showing you, some of you may recognize them as being characteristics of the ZX calculus, which is a particular diagrammatic algebraic approach to quantum computing that's very, initially developed in Oxford, it's still popular in the Oxford-centric part of the quantum information community. So that is to say that we've gone from error correction, and it's motivated what is certainly a heterodox way of describing quantum information theory. Something that at least 90% of computer scientists working in quantum computing don't think about. So, I mean, I'm exhibiting this as sort of an interesting takeaway that just worrying about architecture and how you're going to do error correction has motivated a completely different way of thinking about quantum computing. Not completely unknown before, but certainly not the one that's most common. And in particular, this approach to doing quantum information is very useful because there's a diagrammatic calculus. That is to say, they're not just diagrams. These identity symbols, they are not just declarations. These are actually equations, and that you can reason about these diagrams as a formal mathematical notation. It's not important that you actually draw out the diagrams. It's useful, of course, when you're doing things on the whiteboard. But you get a very nice, simple description of what your procedures look like. You can do, you can prove equivalences and try to do simplifications, and it makes it a very natural tool for compiling, which is the next step up on the chain. We're getting very close to now programming languages and ways that you try to describe algorithms. So, sort of the hopes and dreams of the people who've been working on the ZX calculus in Oxford is that it's a nice abstract category theoretic way motivated for describing quantum algorithms and quantum procedures. So that it was from the start a notion of a theory of interactive classical structures, where you've got two ways of representing and encoding information that are in themselves classical, but they're incompatible with one another because they refer to incompatible bases, incompatible ways of storing information in qubits. And so it's got a very nice sort of abstract pedigree in terms of how you think about it, the philosophical principles behind it, if you like. Maybe this is a way that we can understand quantum computing more easily than previously we did. We just think about quantum computers as operations involving copying in the standard basis. We're not talking about cloning of quantum states, but copying in the standard basis, changes of basis with single qubit unitaries, and parity computations. Maybe this is a way forward. There's just one problem. That this is an even lower level description of algorithms than unitary circuits are. I mean, one of the other features of the ZX calculus is that operations which are primitive in the unitary circuit level, like the control lot, they're composite operations in the ZX calculus. Now that's nice, but that means that what you're taking something which is primitive and you're breaking it down to even more primitive things. It's like taking an AND gate or an OR gate and decomposing it into NAND gates. Which is to say that if you want abstraction, well, from a philosophical perspective, maybe you're making progress. But from an architectural standpoint, you're moving backwards. So the question is, if we want to come up with a high-level way of describing quantum algorithms and programming things, we're going to need to do something else. And the question is, what is it that we should do? ZX is probably going to be a very useful tool for compilers, for automatic reasoning about things, and moving away from this regime of saying, I want to perform a control lot specifically between qubits 70 and 392. You want to have a computer take care of which particular physical qubits you're working with. You want to say, I want to do a control lot between qubits A and B, and let the compiler determine precisely who A and B are, according to what space is available on your hardware. That's what the ZX calculus will be useful for dealing with this task, but for programming, for actually describing new procedures, we're probably going to need something else. And this comes to the last gap. I don't have a solution to this, but I want to sort of point out what the shape of this gap is. So from problems to algorithms, I don't just mean like, I've got a problem, can you solve it with a quantum computer? I mean, that's obviously hard. You're talking about a research problem there. But in terms of even knowing what sorts of ingredients you would use for quantum computers, for classical computers, we've got all of our techniques. We've got dynamic computing, we've got breadth first search, we've got depth first search, we've got memoization. We've got all sorts of techniques that we can apply and that we get some sort of sense for when they're useful. We want a similar box of tricks for quantum computing. The box of tricks that we have is fairly small, is one of the problems. And this is one of the reasons why people are interested in sort of coming up with more abstract descriptions of quantum computing. The hope is that if you come up with an appropriate abstract approach to describing quantum operations, then you might be able to eliminate some of the dross, some of the details, see more transparently, and then come up with new ideas. That's good, but the question is basically where would we expect these ideas to come from? The ideas that we have so far are quantum simulation. So for example, chemistry, having a quantum computer to simulate quantum phenomena in chemistry seems very promising. The adiabatic algorithm is actually a more general thing. It's useful. It's often touted as something that you want to do to solve optimization problems. That's not wrong. But usually it's described also as an approach to hardware as opposed to an approach to actually running one. So this, I mean, it's a natural use case. It's similar to one of the original uses of classical computers to simulate ballistics, such as, say, running a moon mission, so it's nothing to sneeze at, really. But just simulating physics, something direct. It's not the sort of thing where it would be very, very broadly applicable to all the things people would want to use computers for. It's not going to help you with airline scheduling. Eigenvalue analysis, so this is arguably the most famous technique in quantum computing. Eigenvalue analysis, often people would say eigenvalue estimation, only there's generalizations of that. I'm sort of trying to make a broader umbrella to sweep this in under. The idea of trying to find a feature of the problem that, where if you can solve, you think of the problem as defining, say, a unitary operator, a permutation, for example. And if you can find out enough information about the eigenvalues of that permutation operator, then you can find some interesting feature that will solve your problem for you. That's exactly what happens in Shor's algorithm. The order finding subroutine for Shor's algorithm is exactly this. And you may have heard of solving systems of linear equations. So that's something that you can do easily classically. It's something you can do even more easily if you have a quantum computer. You still have an exponential improvement. It's just exponential from polynomial space to logarithmic space. More properly speaking, it's feature estimation for solutions of linear equations, which is a bit of a mouthful, so you can see why they call it solving systems of linear equations. You have amplitude amplification, so Grover's algorithm search. That only gives you polynomial time speed up, but maybe that's interesting. And quantum walks, so there's basically, some people, the reason why I say 3 or 4 known techniques is that some people would say that amplitude amplification is an example of a quantum walk. Quantum walks don't have many applications beyond amplitude amplification. They have a couple. They again only give polynomial time speed ups as far as we know. So it's really the first two that are the really intriguing ones because these are the ones that we expect to give us exponential improvements. And the lower two, well, it depends on how good your quantum computer is, how much overhead you have in getting it to run well. Maybe if you're lucky, not all the speed up has been ed up by your overheads in running your computer. So if you really, really want certainty about usefulness, you're talking about the first two. Or perhaps you'd like to come up with more ideas, but the question is where are they going to come from? You need some sort of way of thinking, what ways are there to access information about my problem that are not available to a classical computer? What features of the problem are abstruse to a classical computer? They might have something like global structure, but it can't just be any global structure. It has to be something that's accessible to a quantum computer. So eigenvalue analysis, if we're talking about eigenvalues of operators, that's referring to diagonalizing an operator. Diagonalization is by unitary transformations. If you wanted to reinvent the idea of a quantum speedup from scratch, that's where you'd start. You take a look, I've got some operator, I want to know something about its eigenvalues. Well, I can get at eigenvalues by unitary transformations, quantum computing. You want to have some sort of similar insight to that for coming up with a new recipe. But failing that, it's not clear where to go with quantum programming and quantum programming languages. Okay, so I mean, a quantum programming language, a good programming language gets out of the way of the algorithm designer. The algorithm designer will have an idea that they want to realize. And the programming language has to make it not only possible, but easy to get rid of bureaucracy. So you're going to need flow control, as usual, like subroutines, recursions, for loops, arithmetic. Not just arithmetic with classical bits, but arithmetic with quantum registers. This is something that's not realized very often in quantum programming languages now, but that's because they're all obsessed with dealing with individual qubits. I think it's time that we probably move a bit further. By moving further, we'll be moving ahead of the hardware, but that's what somebody who's a good theorist should be doing, is moving ahead of what's actually realizable in practice. You're going to want the quantum Fourier transform because it's the one trick that we know is useful, for example, for order finding, for eigenvalue analysis. Most people think that quantum computing more or less consists of the Fourier transform. It's certainly not right, but it's not entirely wrong. So you're going to want that. And you want a way to specify Hamiltonians, for example, for quantum simulation, which is different from saying precisely what you do with those Hamiltonians, but you'll want some sort of Hamiltonian data structure that you can make use of somehow. And then beyond that, I mean, new idioms, basically, it's not a question of what the quantum programming language should provide, it's the question of what quantum programming language should get out of the way. What techniques are there like this that a programming language should make easy? But you can't solve that with a programming language. And that's basically the rest of that gap for problems to algorithms, is finding out the new idioms for coming up with quantum algorithms. All right, so that's it. Thank you for your time.